Welcome to episode 10 of the PlanetSmith devlog. Currently, we use a mesh raycasting system for detecting hexels that has some major drawbacks and is slow. We need a new, faster data raycasting system that will enable us to do cool stuff like this. If this has piqued your interest, come join our Discord, where soon I will be announcing a demo weekend where everyone can play. Also, don't forget to subscribe here on YouTube and add PlanetSmith to your Steam wishlist. It's one of the best ways you can help. At first glance, raycasting may seem trivial, and it would be if we were using standard cubes on a flat plane like Minecraft does, but we're not. PlanetSmith's hexels, that's my word for our voxels, which I have borrowed from this YouTube comment, thanks Nick, are hexagonal prisms and are curved into a sphere, making all the calculations nice and complex. You might be thinking, but isn't this in the game already? How can I not have hexel raycasting when the player can already add and remove blocks from the game? It works, it's functional. Well, this is because I'm using a different type of raycasting, mesh raycasting, which was very easy to set up and only requires a little extra data to get working. However, it has some major drawbacks. Firstly, it only works with blocks that have a collision mesh, as we need a structure to raycast against. This means that you currently can't remove blocks like tall grass directly, or interact at all with water blocks, because of course they haven't got collision meshes. This problem will only get worse as we add more block types that have this property. In theory, we could get around this issue by having two different collision meshes, one for raycasting and one for the player's collision, but this obviously isn't a good workaround, as it doubles the mesh data we have to store and will prevent stuff like interacting with blocks underwater without further workarounds. Also, there is a problem which is more fundamental and stems from the way I detect which block is being interacted with. Currently, when creating the physics mesh, I have this line of code here which encodes the triangle index to the block. This way, when I raycast a block, I can get the triangle number of the hit triangle for a mesh raycast and use that index into my block list. At first glance, this seems fine. However, the game and player are updating at the current frame rate, and the world is only updating 20 times a second. If a player places two blocks inside the same world tick, or breaks two blocks, the indices in the lookup will change, meaning a new block placed will be in the wrong location. This can't really be addressed elegantly. I would have to lock chunks until the update, which would cause some major slowdown to the speed the player can place blocks. What we need to do instead of using this index lookup, which can be outdated, is work out the exact block coordinates and queue that change directly. That way, there can be no mistakes and it doesn't matter how many changes we queue. That's where Hexel raycasting comes in. As we can work out which hexels have been raycast, we can then correctly work out which block is being interacted with and update the world accordingly. This will also, in the future, let us use different tools which will change the context of the raycast so the player interacts with the intended block. Okay, I've putting this off for too long. Let's get started. The first step is to confine the rays to the planet. We don't care about rays traveling off into space, and we don't care about rays that are deeper than our build limit. If we think about raycasting against regular voxels, and just think about the z-axis, up and down, we can look at the start and end of our ray for the maximum and minimum z-value. We know for sure that all other points along that ray will be somewhere in between those two values. However, When we raycast with spherical coordinates, this sometimes might not be the case. This is because the point at which a line becomes tangent with the center of a sphere, the line switches from getting closer to the sphere to getting further away. For example, thinking about the z-axis in our spherical coordinates, say one end is at z equals 12 and that the other end is at z equals 14. We can't be certain that all z values in between are greater than 12 and less than 14. But there's a fix. All we need to do is split our line whenever we cross the tangent point. Then we have two lines, one where all the z values decrease and one where they increase, making our calculations much easier. I now want to break our raycasting down into two separate steps, one which will handle all the intersections with the z-axis and one with the hexagons on the x and y-axis. To calculate the z-axis intersections, I first calculate the z position of the start and end of the ray. The difference between these two values tells me how many z layers the line intersects. I can now use this equation for the intersection of a line with a sphere for each of the layers and store the time of intersection for that later. The time of intersection is how far along the ray the intersection took place. I made a nice raycasting preview in the editor. This lets me visualize how the code is working and helps me catch bugs. Now, for the harder of the two calculations, working out the x and y intersections, where the ray crosses from one hexagon into its neighbor. I start by calculating the x and y position of the ray's origin. Then, create planes for each of these edges of the hexagon. I can then see which, if any, of the edges the ray crosses and the time at which the intersection takes place. From that, I calculate which neighboring tile the ray moved into and repeat the process until the end of the ray, recording all the times, like with the z-axis calculation. Finally, I combine the two sets of intersection data to get the x, y, and z position of each hexel that is intersected and store them in an ordered list from closest to furthest. You can see in the editor all hexels that the ray intersects are correctly detected. We're not done though. We need to determine if any of the hexels should cause a raycast hit. Cycling through each hit hexel in order, we need to transform this position into the memory index where the data for that hexel is stored. If the hexel turns out to be air, it's skipped and the search continues. But if it's something else, the search stops and I can return that hexel. This looks really cool in the editor. You can see I'm raycasting every frame and evaluating what we have hit. It's very accurate and you can see it changing which block is being detected just at the right time. You can also see we can now detect grass blocks and water, something that didn't work before. However, it is treating every voxel the same as a full block. This isn't quite right, as a mesh block or half blocks are smaller than a hexel. We need a way to now raycast against a collider if the block turns out to be one of these special blocks. After a lot of work and a few annoying bugs, like this one, where the collider was misaligned, it's all working. The game now creates triangles to raycast against for any block that is less than a full block. Once a triangle is hit, the rest are discarded and the block is returned for the interaction. I made this cool preview in the editor, which helped me visualize the problem and make sure everything is working as intended. For mesh blocks, this works great and runs super smooth, even when lots of blocks need to be tested. Fence blocks were a bit of a pain to get working correctly, as you need to calculate all the neighbour blocks to determine the shape of the fence block before you can calculate the collisions. Since the collisions are calculated precisely using the triangles, you can interact with blocks through others, allowing for precise control. Perhaps this is a little overkill, so maybe I'll simplify these colliders at a later date to a few bounding boxes, but it works for now. I did tease destruction at the start of this video, and this new technique lets me create something epic. Because we're now looking at the pure data, we can hit voxels that are not rendered in the world. This means I can create a giant laser that instantly destroys everything in its path. This is super fun to play with. Perhaps I'm having too much fun scoring deep scars into the planet. It's also really exciting to see that doing this is causing no lag. Behind the scenes, of course, millions of voxels are being edited and resaved to the hard drive, along with all the mesh changes that are happening instantaneously, creating all the new terrain. After all, voxel games are a kind of magic trick. The world is in reality a thin shell, but when it updates so seamlessly, the world feels as though it's solid and those blocks that are getting revealed were always there. As I let this destruction play out, I'd like to give a huge thank you to all our YouTube members. Your support is now more important than ever, and I appreciate it. Remember, if you want to stay up to date with all things PlanetSmith, come join our Discord, and don't forget to add PlanetSmith to your Steam wishlist. Thanks for watching, and I'll see you in the next video.